Let's start lab02b for phys364, which will let you see what I intended for the in-person version of the voltage divider lab that you just did in Circuit Lab. Let's start with a 1K resistor and a 2K resistor, both of which turn out to be available in the parts drawers right at your workstation. So I will use the ohm meter to check that these resistors are what I think they are. The ohm meter here says 0.987K. So brown, black, brown is 1001. That means 100 times 10 to the 1, or 1K, so that makes sense. So that's our 1K resistor. And the other one we have is a 2K resistor. So let's see what Mr. Ohm meter says. We get 1.979 kilo ohms, so that seems compatible with 2K. Okay, I think if you squint a little, you might see red, black, brown, and then a gap, and then brown for the 1% stripe. So red, black, brown is 2001, which is 200 times 10 to the 1, which is 2000 ohms, or 2 kilo ohms. Then we can turn on the Regal power supply, and it takes a few seconds to turn on. I can push on and say 10 volts. There's 10 volts. But before I do that, let me push this green button again so that it's ready to give us 10 volts, but it's not actually providing 10 volts yet, so that we can have it off while we wire the circuit. I think I'm going to swap this red and this black. So there's a little black jumper wire down here, so that will remind me that I'm using it for ground. So I'm going to use this black side for ground, and I'm going to use the red on top for plus 10 volts, which will sort of resemble our schematic diagram. Here, and I think, okay, so this is the pair of wires coming over from the power supply, so it's going into this row, which I've kind of labeled black with the little jumper wire for ground, and this row, which we've labeled in red with this little jumper wire for positive power. In fact, I think I will even remove this little red jumper wire so that I don't accidentally think that that's my power. And it just so happens that I have a green jumper wire up here. I'll just put the green wire there as a placeholder. So we have 10 volts here. So I guess we want a voltage divider that gives us 2/3 of 10 volts. So R1 is the 1K resistor, and it goes from plus 10 volts to node A. I'm going to use this little column of the breadboard for node A. Then I want one end of R2, the 2K resistor, to go into that same node A, and then node B will be ground. So I'll come down here to ground. So I am taking advantage of the fact that once I plug this in, every hole on this little row is at the same potential. They're all connected together. And in fact, given this jumper, that continues over to this side. And then I can say the same thing up here. So every hole on this little row is connected to our positive power supply voltage. Now I think I probably want to measure the power supply voltage. I mean, maybe I don't really have to measure the power supply voltage because I know what it's supposed to be. Oh, now I have these two little wires. I'm going to put my little pieces of wire into my spring clips. You could just use the spring clip to grab the leg of a resistor. What I like about putting these little pieces of wire, red and black here, is that then I can plug into any node I like without risking pulling a component out. So I'll go from ground to our power supply voltage, and this shouldn't be very well. Right now it reads 0, so it says 0.0. It says 1.8 millivolts. 1.8 millivolts. I'll turn on the power supply, and it should say 10 volts. Okay, 9.988 volts. Okay, so that's my power supply voltage. And then I guess the whole point of a voltage divider is to divide down a voltage. So I should get about 2/3 of 10 volts if I look at node A. So I'm keeping the black lead of my voltmeter at node B, which is connected to ground, and I'll put the red input of my voltmeter at node A, which is between R1 and R2, where R1 and R2 meet, and we see 6.66 volts, which is 2/3 of 10 volts as expected from the voltage divider relationship. Okay, I'll write down VAB, in other words, VA minus VB. So VAB is 6.657 volts measured, and I expect 10 volts times R2 over R1 plus R2, which is, well, using nominal values is 2/3 of 10 volts, or 6.67 volts. I didn't bother to write down the actual measured values of my resistors. I know they're within 1% of the nominal value, so I think as long as I only care about an answer to 1%, I'm going to use the nominal values instead of the measured values. Some people consider it better form to use the measured values, and that is certainly a valid point. But again, because we did measure the resistors and see that they were within 1%, within the 1% tolerance of the nominal values, and we generally only care about results to no better than 1% in this course, using the nominal values is good enough for me here. Next, I want to measure the short circuit current of the voltage divider, which is the current that would flow between A and B if I connected a zero resistance piece of wire between A and B. So if I connect a piece of wire between A and B and I measure the current that flows through that wire, that is the short circuit current. We know that our DMM in milliamps mode has a resistance of about 2 ohms. If I were to connect A and B together with a wire, the voltage drop across R1 would be 10 volts. Now, and this is a 1K resistor. R1 is a 1K resistor. So if I account for the fact that there's a 2 ohm series resistance of the current meter, then I'll see a voltage drop of about 1/500, 2 parts out of 1,000, really 2 parts out of 1,002. I'll see a voltage drop of 2 parts out of 1,002 of 10 volts. So that's 0.02 volts. There would be a voltage drop of 0.02 volts across the ammeter, and then a voltage drop of 9.98 volts across R1. Again, that's a 0.2% deviation, and we're generally content with 1% results in this course. That's another way of saying that for our purposes, the current meter is as good as a piece of wire. But it is worth thinking about the orders of magnitude. So I'm going to use, as we did in the previous lab, this Amprobe AM140A. I guess the instructions ask you to use the 37XRA meter. I'm going to use the AM140A meter instead. So I'll put it on milliamps mode, and actually this is both amps and milliamps mode in the setting for the meter. So on the meter's control panel, this would be both amps and milliamps mode, but we have the red wire plugged into milliamps microamps, not into amps. So that puts us in milliamps mode. Now this is a rare case when using a current meter, I don't have to disconnect anything because we are asked to add the current meter as a parallel path, which is a pretty unusual thing to do with a current meter. Normally, if you add the current meter as a parallel path, you risk running a large current through your current meter. But in this case, we know that resistor R1, the 1K resistor, will limit the current. So the black wire can go into node B, and the red wire can go into node A. Now we see 20 millivolts as the voltage drop across the current meter, which is what I predicted when I was just blah, blah, blah. And we see 10 milliamps flowing through the current meter, and 10.04 milliamps. 10 milliamps makes sense because it is 10 volts divided by 1 kilo ohm. So it seems like our short circuit current, I short circuit, is 10.04 milliamps, and we expect 10 volts over R1, which is 10 volts over 1 kilo ohm equals 10 milliamps. So I measured 10.04 milliamps. I expected 10 volts over R1, which is 10 volts over 1 kilo ohm, which is 10 milliamps. And again, it's just my personality is not inclined to worry about the differences between the measured component values and the nominal component values, as long as we first verified that the actual component values are within our 1% tolerance of the nominal values, because the math is just so much easier with the nominal values. So I measured a short circuit current of 10.04 milliamps. You can see it here, 10.035 milliamps. And I expect a short circuit current of 10 volts divided by R1. I mean, I guess if you really wanted to be precise, it's 10 volts divided by R1 plus the 2 ohm series resistance of this current meter, but neglecting that 0.2% correction, 10 volts over R1 is 10 volts over 1 kilo ohm, which is 10 milliamps. I'm using the nominal values, not the measured values of the components. That's usually good enough for me. One argument I might make in defense of using the nominal values, once you check that the actual values are within the 1% tolerance of the nominal value, is that if you were building 100 copies of this circuit, maybe you're designing it, you want to build a whole bunch of copies of it, then I think what you really want to know is the mean of the distribution for the ensemble of circuits that you build, and not just this one particular circuit. On the other hand, it is often satisfying in a lab to be able to measure things as precisely as you possibly can. So if you do want to check just how precisely you can measure things, then of course you need to measure the precise values of the actual components in your hand. So I think it depends on your emphasis. I'm usually more interested in understanding the idea behind how the circuit works and in checking at the kind of few percent level whether it does what I expect. But it can also be very satisfying if you have the time to work things out to the 0.1% level. I usually feel that working things out to the 0.1% level takes enough extra time in the lab that it's only worthwhile in certain special cases, because I'd kind of like you to be able to move through and see ideas relatively quickly. The next thing we're going to do is to place a variable resistance between points A and B, and that will allow us to measure the output of the voltage divider as a function of the current supplied by the voltage divider. Now, what do we mean by the current supplied by the voltage divider? We want to treat this thing that I just boxed here as a black box, and then we want the voltage measured between these two terminals. That's the voltage output of our black box. And then the current that flows out through here and flows back in through here is the current output of our black box, our voltage divider. So we want to know what is the voltage between these two terminals as a function of the current that flows out this terminal and back in this terminal. And our means of varying that current will be to adjust this load resistor. And then we can measure this voltage and this current together and make a graph of one versus the other. Now, the most convenient way to make a variable resistance is to use a device called a potentiometer. And a potentiometer actually looks just like its circuit diagram representation. You can envision a very long strip of metal that is a pretty good but not amazingly good conductor. And then you have one terminal here, one terminal here, and then there is a thing called the wiper whose position you can vary. So the wiper can move back and forth, and there's a third terminal attached to the wiper. And depending on the knob position, if you turn the knob all the way to the left, then the wiper is connected over here, and the resistance, let's call this A, B, C. They're capital letters. I guess I should choose different, well anyway, they're capital letters. Okay, so if I put the knob all the way to the left, then the resistance between A and B is 0, and the resistance between C and B is the full resistance of my potentiometer. The resistance between A and C is always the full resistance between my potentiometer, as long as there's nothing connected at B. And then if I move the knob all the way to the right, then the resistance between B and C is essentially 0, and the resistance between B and A is the full resistance of the potentiometer, and I can dial anywhere in between. This is how the volume knob on an old-fashioned radio or stereo worked. And if you're used to that kind of crunchy noise, a static noise when you turn the knob, it's because as this wiper moves back and forth across this long resistor, sometimes it's making good contact, sometimes it's making less good contact. So the resistance sort of varies the resistance varies in a sort of complicated way while you're turning the knob, because instantaneously the wiper might be making relatively good or relatively poor contact with this big kind of medium conductor surface. So there are two common ways to use a potentiometer. One is to ignore terminal C and just use A and B, and then you can turn the knob and you get a variable resistance between A and B. Another way to do it is you connect one voltage at A, another voltage at C, and then you turn this back and forth, and by dialing this back and forth, you're essentially varying the voltage that B gets. So it's like you're making an adjustable voltage divider. And then Yet another way to use a potentiometer is to wire these 2 points together, and then you have a variable resistance between A and B. If you turn it all the way to the left, then the resistance between A and B is 0. You turn it all the way to the right, the resistance between A and B is the full potentiometer resistance. You say, why did you bother doing this? And it's because it's a little bit of a subtlety. If the wiper momentarily loses contact, then instead of the resistance between A and B momentarily going to a very large number, like infinity, instead, momentarily the resistance between A and B will just jump up to the maximum potentiometer resistance. That's kind of a subtle point, so you can probably ignore that. So the easiest thing to do is just to ignore terminal C and use terminals A and B. So in other words, the left-hand side and the wiper as your 2 contacts. But it is sort of interesting to think about what's going on inside a potentiometer and the various ways you can use it. No doubt there's a Wikipedia page on potentiometer. Built into our breadboard are a 10 kilo ohm potentiometer and a 1 kilo ohm potentiometer. So today we are interested in the 10 kilo ohm potentiometer, which is labeled 10K pot. So pot is kind of slang or shorthand for potentiometer, and 10K is sort of electronic slang for 10 kilo ohms. And you can see that this pin or this pin will be the left side of the potentiometer. This pin or this pin will be the right side of the potentiometer. And these 4 pins in the middle are all connected to the wiper. So if we use this pin and this pin as indicated on your lab handout, then the resistance between here and here will go from about 0 ohms when this is all the way to the left to about 10K ohms when this is all the way to the right. So I guess we can give that a try. Well, one thing we could do just right away is we could verify what I just said about the resistance between these terminals. Let's take my volt ohm meter. By the way, this thing just powered off. It made a little beep and it powered off to preserve its battery. So when that happens, you have to turn the knob to off and then turn the knob back to the position you were interested in. But now I actually want to go to the ohms position. So that's the 3rd position. So I'll go over to the ohms position. So you see off, then AC volts, which we'll seldom use, then DC volts, which we use all the time, and then ohms. So I'll go over to the ohms position and I'll measure the resistance between this left side of the potentiometer and the wiper of the potentiometer. I'm all the way to the left now and it says 0 ohm. Well, this is pretty bad. Now I go all the way to the right and it still says 0 ohm. Oh, okay. For a moment I got a really confusing result because I was using the red wire of this meter with the black wire from this meter, or maybe vice versa. And that was really confusing. So that's an interesting thing to watch out for. You have to make every mistake once yourself, or maybe you'll remember seeing me do it, to be aware of what mistakes are possible. But you have a red and black pair of wires here, and you have a red and black pair of wires here. And I just did a kind of classic mistake where I took the red wire from one and the black wire from the other, and I got results that I didn't understand. I'll also turn this off to preserve its battery for a moment. And now let's go from the left end of this potentiometer to the wiper, and I see 0.2 ohms, 0.1 ohms now, 0.1, 0.2 ohms. I'm all the way to the left. I'll go about 1/3 of the way up. Okay, that says about 3 kilo ohms, just under. I'll go about halfway. It says about 5.4 kilo ohms. I'll go all the way to the right, and it says 9.564 kilo ohms, 9.56. So this is clearly not a 1% component. But anyway, that's not bad. So it's like decently close to 10 kilo ohms. So it's sort of a nominally 10K pot, but it's not anywhere near 1%. I guess it's more like, this is probably a 5% component. In the old days, 5% components were pretty common. So this seems to be a 5% tolerance 10K pot. Okay, so we can see that we can make the resistance between here and here go from 0 to around 10K and to basically anything in between by dialing the knob between the leftmost and the rightmost orientations. So now back to our circuit. Turn this meter off for a moment to save its battery. And it seems as if I need a couple of pieces of wire. I want to go from this point in the circuit to one end of the potentiometer, and then I want to go from this point in the circuit to, let's say, the wiper of the potentiometer. And then I can dial the knob back and forth to adjust this resistance and thereby adjust the current. And then meanwhile, I want to set up to measure this current and to measure this voltage. Let's see how we're going to do that. So I think I will make myself a roughly 10 centimeter long piece of yellow wire, and I'll strip a few millimeters of insulation off of each end, and I'll make myself a roughly 10 centimeter long piece of blue wire, and I'll do the same thing, strip a few millimeters of insulation off each end, and then I'll go from, here's node A, I'll go from node A to the left end of the potentiometer, and I'll go from node B, which is ground, to the wiper of the potentiometer. I want to set up my voltmeter, so this is the one I'm using as a voltmeter. So I want to set up my voltmeter to measure the potential difference between node B, which is ground here, and node A, which is this little column. And then I want to set up the current meter, which I need to unplug from here. I want to set up the current meter to measure the current either flowing out of this node or into this node. To do that, I have to break a connection somewhere. I'm going to do that by measuring the current that flows through this new wire that I just inserted. I'm going to break one of the connections to the potentiometer. That seems like the thing to do that's consistent with this schematic diagram. This yellow wire is going from this point, node A, between R1 and R2, down to the potentiometer. So I'm going to interrupt this yellow wire, and I'll run it over to this kind of miscellaneous unused node over here. I'll put the red wire of the current meter at that point, and it occurs to me now that I didn't really need the yellow wire. I could have used the current meter in place of the yellow wire, but we'll just keep going. And then I'll put the black lead of the current meter into this left-hand side of the 10K potentiometer. So here's my 10K potentiometer. So now the wiper, this middle thing, the wiper is connected to ground, which is the same as node B in our schematic diagram. The left side of the potentiometer is connected to the black end of the current meter. The red end of the current meter is connected to this yellow wire, probably unnecessarily, which then goes over to node A coming out of the voltage divider. And I guess I could have just bypassed the yellow wire and put the red wire of the current meter directly into node A here, if I had been thinking ahead. Okay, now let's put the voltmeter in DC volts mode, and let's put the current meter in milliamps mode. And right now, the resistance of the potentiometer is programmed to be close to 0 because the knob is turned all the way to the left. So we're getting a result pretty similar to our short circuit configuration. The current through the current meter is 10.03 milliamps. The voltage between nodes A and B, so the voltage output of the voltage divider, is 24 millivolts, 23.7 millivolts. So I guess I can say I want to make a little table. Well, before I draw a diagram, I might make a table. Well, I guess we can make a graph. Okay, on this graph, current 10 milliamps, that seems to be as far to the right as we want to go. And the voltage is 0.02 volts, which basically looks like 0 on this graph. Now I'm going to turn the knob to the right until the current goes down to 9 milliamps. That's pretty good, 9.01 milliamps on the current meter. The voltage meter reads 0.689 volts, 689 millivolts. So, okay, so we have 9 milliamps and we have about 0.7 volts. Then I'm going to turn the knob on the potentiometer to the right until we get about 8 milliamps. Okay, so at 8.02 milliamps, which is close enough to 8, I'll call it 8, we have 1.34 volts. Then I'll turn the knob until I get 7 milliamps. Well, 6.99 is close enough for me. Well, okay, 7.00. So then I get 2.023 volts. So I'm going to call that 2 volts on my graph. And then I'll turn the knob to the right a little bit until I get 6 milliamps. Okay, and then I get 2.61 volts. So 6 milliamps, 2.61 volts. I'll keep turning the knob to the right until I get about 5 milliamps. Now this is getting a little bit dull. So if I were using real precious lab time instead of YouTube time, I would skip and do 2 milliamp increments instead of 1 milliamp increments. But it's easy for you to fast forward, so I'll go slowly. This is 4.995 milliamps, basically 5 milliamps, and I get 3.35 volts. Then I'll go down to 4 milliamps by turning the knob to the right on the potentiometer, and I get 4 milliamps of current and 4.06 volts. Keep increasing the resistance of the potentiometer until I see about 3 milliamps. Okay, 3.01 is close enough for me. And we get 4.66 volts. Then I'll keep increasing the resistance on the potentiometer till I get 2 milliamps. And okay, 2.05 milliamps, I get 5.3 volts. Then I'll keep going up until I get about 1 milliamp, and I get 5.99 volts, basically 6 volts. 1 milliamp, 6 volts. And then let me turn this thing all the way to the right. Well, I guess the best I can do is 0.6 milliamps. I guess, okay, 0.6 milliamps. Well, I know what I would get for 0 milliamps, right? So if I just completely unplug the yellow wire, I pull out the yellow wire, then I have 0 milliamps flowing, and I get 6.65 volts, which was what I got earlier. So my graph looks like this. The short circuit current is 10 milliamps, and the open circuit voltage is 2/3 of 10 volts, about 6.66 volts. And then I have a nice straight line in between, and the slope of this line turns out to be 667 ohms, which is R1 parallel R2, well, minus. So the slope of this graph is what we call minus R Thevenin. So R Thevenin for this circuit, which is the output, well, we can also call it the output resistance, the Thevenin resistance, is R1 parallel R2, which is 1K parallel 2K, which turns out to be the same as 2K parallel 2K parallel 2K. It's 2/3 of a K, or 667 ohms. So this slope is minus 667 ohms, as you can verify. So the slope we got, which turns out to equal minus R Thevenin, is minus 667 ohms, which will turn out to equal R1 parallel R2. The open circuit voltage is 6.67 volts, which turns out to be the same as the supply voltage times R2 over R1 plus R2. The short circuit current is 10 milliamps, and this is an interesting fact. This will turn out to be the same as V open circuit divided by R Thevenin, and you can see 6.67 volts divided by 667 ohms is 0.01 amps, or 10 milliamps. That also turned out to equal V supply divided by R1. And so you can work out the math to show that that also is true. Well, here, I'll save you a little bit of work. So V open circuit, we said, equaled V supply times R2 over R1 plus R2. That's the voltage divider equation. So I can write that upstairs. Downstairs, I can say that R Thevenin equals R1 parallel R2. So that R1 parallel R2 is R1 R2 over R1 plus R2. The R1 plus R2 will cancel, the R2 will cancel, and we'll get V supply over R1, which is what you would have said this short circuit current is just looking at the schematic diagram and not thinking too hard about Thevenin models. You would have said, oh yes, it is the power supply voltage divided by that first resistor because the second resistor is shorted out. The next instruction asks us to zero the power supply voltage. Now, you actually can leave the power supply on and set its voltage to 0, which is what the instructions ask you to do. But I prefer to think of a 0-volt battery as a wire. A battery that supplies 0 volts is a wire. So I am going to replace the power supply with a wire instead of following the stated procedure. And then I'll do what it asks and measure the resistance between point A and point B. So I happen to have here left over this little piece of yellow wire that we were using earlier. So I'm going to remove, well, first I'll turn it off. I'm going to turn off my DC power supply here. I'll pull out the two wires, and then I'm going to replace the DC power supply with this piece of yellow wire. So I have a piece of yellow wire going from this little row that I've been calling 10 volts to this little row which I've been calling ground. So it's just replaced by a wire. Then I have a current meter plugged in here and a potentiometer. So I want to remove that so that I don't confuse myself. I already confused myself by mixing up the two red leads for the two multimeters. Okay, now I have just this one meter and I want to put it into ohms mode, and I want to measure the resistance between node A and node B. Oh, I'm also going to remove this little piece of blue wire that we're not using. Okay, so we have our voltage divider as originally built. So here is our 1K resistor going from the supply voltage to node A, and here's the 2K resistor going from node A to ground, which we're also calling node B. But instead of the power supply, I just have a piece of wire, because a 0-volt power supply is just a piece of wire. Not only that, but you're going to see you will soon see that a trick for getting the Thevenin resistance is to replace all voltage sources with wires. So let's actually do that. We'll replace this voltage source with a wire. And then we'll measure the resistance between node B and node A. And we see 662 ohms, which is pretty close to our expected 2/3 of a K. So I see 662 ohms, and I expected 667 ohms, or 666.7 ohms. So that's pretty good. That's within 1%. So I think that's pretty cool. Okay, that was part one of lab02b. Okay, let's move on to part two of lab02b. We are going to take an old-fashioned analog meter movement, whose mechanism is sort of magnetic in origin. There's a little diagram kind of illustrating how it works. So a current flowing through a little coil of wire creates a magnetic north and south pole, and that little magnetic moment can then be deflected by the field of a permanent magnet. And there's also a spring, so then the position of the pointer depends on the magnitude of the magnetic field created in the little coil of wire that a current flows through. So essentially you get a deflection of this pointer which is proportional to a current flowing through this little black and red pair of wire. A key idea we're going to use, by the way, is you saw that two resistors wired in series form a voltage divider, and by contrast two resistors wired in parallel form a current divider. So we will use this current divider idea. In the old days, before everything became digital, before we had these handy digital multimeters, people actually used analog multimeters. This thing is called a VOM, volt ohm meter, and I think you heard me in the first lecture use the outdated phrase volt ohm meter instead of saying digital multimeter. This thing is not electrically powered. It doesn't need a battery. And its internal mechanism works by measuring currents by creating a magnetic field with a current flowing through a little coil of wire. And that magnetic field has the effect of deflecting this needle. So fundamentally it's a current measuring device. And then if you want to measure a voltage, you measure the current through a known resistance. And then if you want to measure a current, you can just make that current flow directly through the meter. Although if you want to change scales, you can use a resistor in parallel so that only a fraction of the applied current runs through the device that deflects the meter, so that gives you a mechanism to change the maximum current reading on the scale. And then I'm no longer completely certain about my statement that this contains no battery, because it is capable of measuring electrical resistance. To measure a resistance, it would have to supply some kind of a voltage. So you want to think of this device as a perfect current measuring device, an ammeter, with some small internal resistance in series. In reality, it is the coil of wire that has this internal resistance, but in drawing schematic diagrams, we often take a real life object and represent it as some series or parallel combination of idealized objects. So our real life current measuring device will be an ideal current measuring device in series with some resistance that we want to measure. Now, in actual real life, we have protected this device against being burned out by excessive voltages by putting a back-to-back pair of diodes in parallel with this series combination. And we sort of got a glimpse in the previous lab of how a diode behaves, but we won't really get to know diodes until the next week or so. So a current cannot go through a diode backwards. A current, if it flows through this diode, will only go this way. A current, if it flows through this diode, will only go this way. And a current will not flow through this downgoing diode until the voltage at A is at least about 6 or 7/10 of a volt larger than the voltage at B. And current will not flow through this upgoing diode until the voltage at B is at least 6 or 7/10 of a volt higher than the voltage at A. So as long as we keep the voltage difference between terminals A and B smaller than about 6/10 of a volt, the diodes will both be off and we can ignore their presence. So they're there just to switch themselves on in case we apply a voltage between nodes A and B that would be big enough to burn out the little meter. So we're going to start by measuring the internal resistance of this contraption. Probably the easiest way to do it is just to use the ohms feature of our digital multimeter. So let's do that. Okay, I'll take the two leads of my digital multimeter that we've been using for measuring volts in recent labs. I'll take the little pieces of wire off of the spring clips. I'll put this thing in ohms mode, and then here's our little meter movement. So I'll grab one end with the black lead and I'll grab the other end with the red lead. It seems as if that runs that's interesting. I'm going to connect it the other way so that the ammeter meter movement reads a positive value. So it seems as if connecting the black lead to the red wire and the red lead to the green wire produces a positive number. It seems like this claims to be, now we're supposed to take this as a totally uncalibrated device. We're not supposed to know that this is a milliamp. But it seems as if our ohm meter is running a current of about 0.1 milliamp or 100 microamps through this device in order to measure its resistance. Like so. And by the way, a digital multimeter is fundamentally a voltage measuring device. So to measure a resistance, this digital multimeter runs a small known current through the unknown device and then measures the voltage across that unknown resistance to infer the resistor value. So it seems as if our resistor value is about 124 ohms. So we'll write that down. It seems as if the internal resistance of this meter movement is 124 ohms. Now the instructions tell us not to bother doing so, but I think if we really wanted to confirm that this full-scale current reading really is a milliamp, now that we know that the series resistance is 124 ohms, I think we could take the 1K resistor that we were using earlier and put it in series with this meter movement. So I can make a little voltage divider. I can go from, this thing is still off while I'm wiring things up, but I could put some known voltage here, and then we can go through this 1K resistor, and then we're going to go through this meter movement, and then we'll go down to ground and back into the power supply. And I guess I know that this is 1000 ohms and this is 124 ohms. So together in series, that's 1124 ohms. So I think if I program this power supply for 1.124 volts, I should see a 1 milliamp current. Let me try that. So let me say 1.124 volts and turn it on. Now it seems as if I deflected the needle the wrong way. So let me turn this back off and reverse this so that I have the red lead at the more positive voltage and the green lead at the more negative voltage. And then I'll turn this back on. Well, that's pretty good. It seems like I can't say for certain that it's not off scale. It looks as if it's right about 1. Let me turn this down just a little bit to convince myself. Okay, so there we go. So at 1.124 0.09 volts. I see 1 milliamp here. So it seems as if at the level of a few percent, this is indeed a 1 milliamp full scale. For this exercise, we're kind of only interested in the roughly 10% scale. So now that I know that our little contraption here can measure 1 milliamp and it has a series resistance of 124 ohms, we want to figure out how to connect one or more resistors to this device so that we kind of create our own little black box, and when 10 volts is applied to that black box, the needle deflects fully, and let's say if 5 volts is applied, then the needle deflects halfway, and if 2.5 volts is applied, the needle deflects a quarter of the way, and so on. I think the easiest way to do that is simply to take a 10K resistor. So here is a 10 kilo ohm resistor, and to put it in series with our little meter movement. And you know our little meter movement looks like a perfect ammeter and 124 ohms in series with that. And then this big combination will be our kind of black box that we are calling our voltmeter. You see, so we're pretending that we're going to build a device and put it inside this box and sell it. And we're going to claim that it is a voltmeter whose full scale voltage is 10 volts. And if we look inside the little black box that we build, it is a 10 kilo ohm resistor in series with this little contraption we've been handed. And again, we're kind of only interested in 10%-ish accuracy for this project. So, you know, in reality, this won't be 10 K ohms. This will be 10.124 K ohms. But that is a 1% effect roughly, right? About a 1.25% effect, because the difference between 10 kilo ohms and 10.124 kilo ohms is 1.2%. So let's see if that works. Let's wire that up. So we're pretending, you know, that we build a little box around this thing and it just has these two external leads to the outside world. Okay, so I need to reach into the parts drawer over here and find a 10K resistor. And then I'll use our modern digital multimeter to check that this is really a 10K resistor. So I will go into ohms mode, and this is, the black wire is always in the common input, and the red wire will be in the volts ohms input. And I will measure the resistance across this ostensibly 10K resistor. Oh, and the stripes, it's really hard to tell which stripe is the brown 1% indicator. But you can see, I think, that we have brown, black, black, red, and then there's the brown stripe that says 1%. So brown, black, black, red is 1002. So that's 100 times 10 to the 2. 100 times 100 is 10,000 ohms. So it makes sense that this should be a 10K resistor. And the ohm meter says 9.92K, 9.93K. Okay, so that is within 1% of 10K. Very good. So we'll take our 10K resistor, and then we'll remove this 1K resistor we were using earlier just to check the full scale current. And this red wire up here is coming from the positive voltage from the DC power supply, which currently is off. So that will be distributed along this horizontal row. And then this red wire is, I guess, the positive input of our meter movement. And this green wire is the negative input of our meter movement. So this negative input we will connect to ground. So this black wire down here is the ground wire from our power supply. So I'll put our 10K resistor between this upper row and the input to the meter movement. And then the claim is, if I program the power supply for 10 volts, this thing should say full scale. And if I program the power supply for 5 volts, it should say half scale, and so on. So let's zoom in so that we can see that. Okay, this row is the positive voltage wire coming from our DC power supply, which is currently off. Down on the bottom, this lower row, this little black wire, is the return, so basically the ground coming from our DC power supply. Then going from our positive voltage to this little column is a 10K resistor, and then going from this little column to ground is our 1 milliamp meter movement, which we know has an internal series resistance of 124 ohms. So if we put 10 volts from here to here, we expect within about 1%, we expect 1 milliamp to flow through this circuit and to deflect this meter movement to the end. So let's give that a try. So we'll do 0 volts. So now this thing is set for 10 volts. Now I can push the on button, and it now tells me that it really is providing 10.00 volts. And this thing is at full scale. Now we might be suspicious whether the reading can be trusted when it's just a tiny bit beyond full scale. So let me turn the knob just a little bit to the left so that we're just a little bit below full scale. It seems as if we're right at full scale at about 9.9 volts. That's good enough for us. For this measurement, we only care about kind of the 10% level, and that seems as if it's within the 1% or so level. Then we can go down to 5 volts. So this says 5.00 volts, and we see we're at half scale, and then we could go to 2.5 volts. This says 2.5 volts, and we're at a quarter scale, and we can go to 7.5 volts. So this says 7.5 volts, and we're at 3/4 scale, so that seems to work. So it seems as if we did what we intended to do. Basically, we put a 10K resistor in series with this current measuring device, and because we know that this device reads full scale when a milliamp flows through it, at least plus or minus a few percent, this 10K series resistor creates a voltmeter whose full scale voltage is 10 volts. So that is indeed how an old-fashioned VOM changes voltage scales. It changes the series resistor that it plugs in when you want to go from the 10 volt scale to the 1 volt scale or the 100 volt scale and so on. By the way, what is the input resistance of our complete voltmeter? It seems like it's 10K ohms, right? Or 10.125K ohms. It's basically 10 kilo ohms. That's a lot less than the 10 mega ohms input resistance of a modern digital voltmeter. And this is one of the real drawbacks of these old-fashioned VOMs. In addition to reading out less precisely than a digital voltmeter, it does not have the benefit of this gigantic input resistance that we've become accustomed to with digital multimeters. And that means that when using an old-fashioned volt-ohmmeter, one really had to be much more aware of the limitations of the instruments than we do when we're spoiled by these modern digital instruments with their gigantic 10 mega ohm input resistance. The next thing we want to do is to turn our little meter movement, which we know out of the box has a 1 milliamp full scale. We want to turn it into a current meter whose full scale is 10 milliamps. Well, that means we basically want a 10-to-1 current divider, so that 1/10 of the applied current runs through the meter movement and 9/10 of the applied current runs through the desired resistor. So let's think about how to do that. I think if we take our milliammeter, basically our little meter movement whose full scale is 1 milliamp, and we know its internal resistance is 124 ohms. So if we create a current divider, two resistors in parallel form a current divider. And if we have a 9-to-1 ratio, so if this is 9 times as large as this, then I think 1/10 of the current will flow through here and 9/10 of the current will flow through here. You expect more current to flow through the smaller resistance, less current to flow through the bigger resistance. So you should convince yourself that if we have a 9-to-1 ratio of resistors, then 1/10 of the total current will flow through here, 9/10 of the total current will flow through here. Let's see how close we can get to 13.8 ohms in the back room. It so happens that in the back room we have a 12 ohm resistor. So this is brown, red, black. And then there's a gold stripe. I think the gold stripe means 5%. So this is 1, 2, 0. So that's 12 times 10 to the 0, 12 ohms. Let's try measuring this with the ohm meter. So I'll turn the ohm meter on to ohms mode, and then let's see what we get. It says 12.6 ohms. I think that's close enough for our purposes to 13.8 ohms. Yeah, it's different by about 10% from what we want, so I guess I would say close enough. And we want to put that in parallel with our meter movement. So let's see. Here's my 12 ohm resistor. I'll pull out this 10K resistor, and I will put this, one end goes at the positive end of our meter movement, the other end goes at the negative end of our meter movement, which is still plugged into ground. Now we need somehow to arrange for a 10 milliamp current to flow from this terminal down to ground. So the way we could arrange for a 10 milliamp current to flow, by the way, so the parallel combination of these two resistors, 13.8 ohms in parallel with 124 ohms, will be 12, well, it's not really 13.8. I guess this actually turned out to be 12.2. But anyway, 12 parallel 124 is going to be a little bit less than, it'll be about 10% less than 12. So this will probably be about 11 ohms. So this is about 11 ohms in parallel. 12 ohms in parallel with 124 ohms is about 11 ohms. See, this is about 10 times bigger than this. If this is 10 times as big as this, then these two things in parallel are this smaller thing minus a tenth of the smaller thing, because this is 10 times as big. So it should be 12 ohms. It should be about 10% smaller than 12 ohms. So it should be a little less than 11 ohms, these two things in parallel. I guess we could directly check that with the ohm meter. Let's just directly check that with the ohm meter. We'll put this in ohms mode, and we can say what is the resistance from this point in the circuit, which is the upper end of our meter movement in parallel with the upper end of our shunt resistor, and then we'll go to the bottom end of both, which also turns out to be our circuit ground, but it doesn't matter that it's our circuit ground because the power supply is not connected. And we see 11.4 ohms. Okay, so that's about what we expected. Let's see, and this all by itself was 12.6 ohms. I see, 12.6. Okay, plug it back in, we get 11.4 ohms. I guess you want to work out for yourself that 12.6 ohms in parallel with 124 ohms is about 11.4 ohms. Now we want to arrange for 10 milliamps to flow here so that we can check that this is really full scale, 10 milliamps. We can check that our new black box here has a full scale deflection of 10 milliamps. I think the easiest way to do that is to put a 1K resistor here. So if we have a 1K resistor and we connect the power supply between these two terminals and we program the power supply for 10 volts, this is 10 volts divided by 1.01 kilo ohms, right? So you do have to ask, what is this resistance you're putting in series with the 1K resistor, to ask, are we really getting 10 milliamps? But this is 1K plus the parallel combination of these things. The parallel combination of these things is 11 ohms. So that's 1.01 kilo ohms. So if we program this for 10 volts, this will be within a percent or so 10 milliamps. So let's find a 1K resistor. Brown, black, black, brown. This is the brown, black, black, brown. This is the 1K resistor we were just using a moment ago. So I will put it from this point in the circuit to the positive power supply voltage. So that ought to work. Then I'll get rid of the ohm meter. I don't want the ohm meter to affect our measurement. And let's see if we put this on 10 volts, 0 volts, and then we'll turn it on. And sure enough, we get basically full scale deflection. I guess to get exactly full scale deflection, turns out we go to about 10.6 volts. But anyway, again, we only care about kind of 10%-ish level for this exercise. So it's basically full scale at 10 volts, which would be 10 milliamps because we have basically about a kilo ohm in series. And then if we get down to 5 volts, then we get half of full scale. How do you know that we really have 5 milliamps flowing through there? I guess if we really wanted to, we could interrupt this circuit, and then we could uninterrupt it using the current meter. So here is the other handheld meter that we've been using as a current meter. So this is in milliamps mode, and then I can go from this end of this resistor and complete the circuit to this point. So I basically broke this circuit at this point between the 1K resistor and our little 10 milliamp black box. And then I'm going to re-complete the circuit with the current meter. And sure enough, we see 5 milliamps. And if I go up to 10 volts, then we see 9.93 milliamps, and our little meter movement here measures 9.5. And we can go down to, I don't know, we can go down to 3 volts, and we see 2.98 milliamps on the digital meter, and we see just below 3/10 of full scale on our meter movement. So I guess we succeeded. Does your current meter work as advertised? I guess it does, plus or minus a few percent. How did you check? We ran a known current through it. What is the input resistance of your ammeter? Well, we actually had to determine that. It was about 11 ohms. For comparison, right, the AM probe 37XR ammeter reports an input resistance of 10 ohms on the milliamp or microamp scale and 0.035 ohms on the amp scale. And then this device, it turns out, appears to have about a 2 ohm series resistance on the milliamp scale. So the input resistance of this current meter is 2 ohms, it seems. But the input resistance of this little 10 milliamp meter that we just built ad hoc is about 11 ohms. Okay, that was part 2. Okay, the next exercise is the voltage divider. First, we want to draw a schematic diagram for a voltage divider that will take 3.0 volt power supply input and will provide a 2.0 volt output using 2 resistors whose values add up to 3 kilo ohm. I think we know how to do that. So we want the output to be 2/3 of the input. So I think we want the power supply to be here, and this will be 3.0 volts, and then we want a 1K resistor here and a 2K resistor here, and this will be our output, and we're going to call this the ground. Okay, so let's build that, and we're going to try to build it so that the actual physical circuit resembles the schematic diagram. Well, while we're zoomed in on the power supply, let's set the power supply to 3 volts and turn it on, and it says 3.00 volts. So let's take the 1K and 2K resistors we were already using before. So I think you can just barely see that the one on top is brown, black, black, brown, and then there's the 1% brown stripe. And the one on the bottom is red, black, black, brown, and there's a 1% brown stripe. So brown, black, black, brown is 1001, which is 100 times 10 to the 1. That's 1000 ohms. And then red, black, black, brown is 2001. That's 200 times 10 to the 1, so 2000 ohms. We could measure them again, but we measured these very same resistors half an hour ago, so we can just use them. From the DC power supply, we have this red wire carrying plus 3 volts and the black wire carrying ground going to the upper and lower rows on the breadboard. So I like to do positive voltage up here and ground down here. Later you might do an even more positive voltage, like plus 15 volts. I like to do that way up at the top, and later you might do a negative voltage like minus 15 volts, and I like to do that down here, but different people have different conventions they like to follow. So we'll take our 1K resistor and bring it from the positive supply voltage to some intermediate point. So I'll just use this column as this node, the output node of our voltage divider. So basically, you see the relevant nodes here are, there are really 3 nodes in this circuit. This node is connected to the power supply. This node will be the output of the voltage divider with respect to ground, and this node is the ground. In principle, a Thevenin theorem device has 2 terminals, but we're taking one of those terminals to be ground. So if we draw a little black box around something to make a Thevenin model, you want that little black box to have 2 terminals, but here's one terminal, here's the other terminal. So we're going to use ground as one of them. Okay, here's the 2K resistor. So we'll go from this output node to ground, and I believe the power is still on, so this should be 2 volts if we measure it with the voltmeter. So here's Mr. Voltmeter. I can put him into volts mode, DC volts mode, and again the black wire is in common the red wire is in volt or ohm mode. That's where it stays for everything except measuring currents. So these two ports are for measuring currents. Now, it would be the simplest thing for me to do is to connect the red wire, the red spring clip here, and the black spring clip here, and that gives me 2 volts, 1.996 volts. I usually think it's a little nicer to use a piece of red wire and a piece of black wire so that the voltmeter can directly probe the breadboard, and then I can move around easily from place to place on the breadboard, even if I want to probe something that doesn't have convenient component to grab on. So you'll develop your own lab habit, work through the lab. So you don't have to use my habits, but I'm going to be a little bit didactic about explaining my habits so that you can assess them and decide whether or not you want to follow them. Okay, so now build your circuit on the breadboard, check. As you did before, try to arrange the components, they resemble the arrangement of the components in your schematic, check. Oh yeah, so we did that in fact. So our schematic diagram looks like this, and you see here is 3 volts up here, and then this 1K resistor, we kind of made this go horizontally, and then this 2K resistor kind of goes vertically, and we put this output node over here. So I did try to make it resemble my schematic diagram. I find it much more legible if I do that. Okay, supply plus 3 volts the input of the divider, check. Measure V out, check. Measure the short circuit current. Okay, well, to measure the short circuit current, I'll take our second meter, and it is already set up to measure milliamps. So here's our second meter. The red wire is in the milliamp receptacle. I'll turn it to the milliamp setting. Notice that it beeps at me if it's wired for measuring current and I'm not on a current measuring setting. Okay, so it is configured to measure current. As we said earlier today, measuring the short circuit current of your circuit, of your, well, Thevenin circuit or of your voltage divider is one of the few examples where you don't have to unplug anything. You don't have to interrupt an existing circuit to measure the current, because you are adding a path that did not exist before. Whereas normally when you measure a current, you're measuring the current flowing through some path that is already connected, so you have to disconnect it and then reroute that current to flow through your meter. So we want to measure the current flowing out here and back in here when we make this just be a wire. So that's easy to do. I'll just put the red lead of the current meter at this output node, and I'll put the black lead at ground. Notice that abruptly the voltage output of the voltage divider, when I do this, when I make this final connection, it should drop to approximately ground, because it would be 3 volts times the 2 ohm series resistance of this current meter divided by that 2 ohms plus 1000 ohms. So it's 2 over 1002. It's basically 2 parts in 1,000. 2 parts in 1,000 of 3 volts. So that will be 6 millivolts. So I think we should read, instead of reading 2 volts, I think we're going to read 6 millivolts when we connect this. Ideally, we should read 0 if it were really a wire, but in order to measure the current with this digital multimeter, the way this digital multimeter works, fundamentally it measures voltages, so it is going to put this small resistance between its 2 inputs, and it's going to measure the voltage drop across that small resistance. That's the way it measures currents. So it puts a 2 ohm resistor between its 2 inputs, and then to measure the current flowing through that 2 ohm resistor, it measures the voltage across the 2 ohm resistor, and then it tells you what its inferred current is. So I think we're going to see 6 millivolts here. I haven't tried this before. Oh, look at that! 6.2 millivolts. And we see 3 milliamps. So we have I short circuit equals 3.0 milliamps. And the fact that this reads 6 millivolts basically just tells you, it's just a reiteration of the fact that the input resistance of this particular current meter is 2 ohms when we're on the milliamp scale. By the way, we expected the output voltage, originally the open circuit, so V open circuit, so that's when we were not drawing any current from here. We expect that to be our power supply voltage, which was 3 volts, and then times this bottom resistor, which is 2 kilo ohm, and then divided by the sum of these 2 resistance, which is 3 kilo ohms. So that's 2/3 of 3 volts, which is 2 volts. So that's what we saw. And then just looking at the schematic diagram, when we put a wire between this point And this point, current that flows through that wire should be 3 volts divided by 1K is 3 milliamp. And that is indeed what we see. And then what we're calling a wire, just because of the features of this particular digital multimeter, what we're calling a wire is actually a 2 ohm resistor in this case. So what we saw here became 2 ohms divided by 2 ohms plus 1,000 ohms. So this voltage became 6 millivolts, but that's really only telling you something about the meter. It's not really telling you anything about the circuit itself. Using your measurements above, determine V Thevenin and R Thevenin, the Thevenin equivalent voltage and resistance for your voltage divider, where the 2 terminals referred to in Thevenin's theorem in this case are V out and ground. Well, V Thevenin is the same thing as V open circuit, which we measured to be 2 volts. And R Thevenin turns out to equal, for reasons that I hope are somewhat familiar to you from the reading, R Thevenin turns out to be V Thevenin divided by I short circuit. And we measured I short circuit to be 3 milliamps. So this is 2.0 volts divided by 3.0 milliamps, which is 2/3 of a K, or 667 ohms. 2/3 of a kilo ohm, 667 ohms. The second method to determine R Thevenin, which you should try as well, is to zero the input voltage. Actually, I prefer to replace it with a wire, and we did this earlier for a different circuit, but let's do it now. So I will turn off power supply, and I guess I'll pull this out. I shouldn't have to pull it out if it's turned off, but I'll do it anyway just in case I turn it back on and I'm not thinking. And I will take this little yellow wire and put it in place of the power supply. So now we've replaced the power supply with a short circuit with a wire, and let me turn off, remove current meter. So this is a voltmeter between the output and ground, but I want to measure the resistance between the output and ground. So I'll just take this voltmeter and turn it to the ohm setting, and it tells me 662 ohms. Okay, so we measured R Thevenin, measured directly, was 662 ohms. And I can try to make my omega more like a capital omega. I realize now that I should probably merge the best parts of part 1 and part 3's lab for future years. Now load the voltage divider with a 100K resistor. That is, we want to put a 100K resistor. So our voltage divider looks like, here, I'll turn this meter off so that it doesn't drain its battery while we're thinking. So this is our voltage divider. So we envision our voltage divider to be this black box with these 2 terminals as its outputs, and this terminal is connected to ground. And this is what we've been calling V out. We pretend that this is a little box whose inside we can't see, but this is some box which is parameterized by V Thevenin and R Thevenin. Those parameters, V Thevenin and R Thevenin, characterize the IV curve of this device. So if you draw no current from it, then the output is V Thevenin. And if you want to know how quickly does the output voltage decrease as you draw more and more current from it, the slope of that IV curve equals minus R Thevenin. So we get an IV curve that looks like this. Here is V out, here is I out. And this current is I short circuit, and this voltage intercept is V open circuit, which equals V Thevenin, and this slope equals minus R Thevenin. So we are now going to put a load resistor. This is R load, which in this case will equal 100 kilo ohms between V out and ground. 100 kilo ohms is much, much larger than R Thevenin. So I think that this will make a pretty small difference in V out. You say, how small a difference? I think instead of 2 volts, I will see 2 volts times 100 kilo ohms divided by 100 kilo ohms plus 667 ohms. So if we turn the voltmeter back to volts mode, and we turn the power supply back on, I'm going to remove my yellow wire, and I'll plug the power supply back in, and I'll turn the power supply back on. So the power supply is supplying 3 volts DC, and we see 2 volts, well really 1.997, but that's pretty close to 2 volts. So I claim that this 1.997 volts will be multiplied by a factor of 100K divided by 100.667K. That's a factor of 0.9934. So if I take 1.997 and I multiply it by that factor of 100K divided by 100.667K, I get 1.984 volts. So I claim that this 1.997 volts will become 1.984 volts when I put a 100K resistor in this position. So happens we have a 100K resistor right in the drawer at our workstation. So the pattern is brown, black, black, orange, and then there's the brown 1% stripe. Brown, black, black, orange. So orange is 3. So you say black, black is 0, so black. Brown, R-O. So orange is 3, so it is 1003. So that's 100 times 10 to the 3. So I think when I put this 100K resistor between V out and ground, I should see this 1.996 volts become something like 1.984 volts. Let's see. So here's the V out node, and here is ground. So this column here is the V out node, and this row is ground, and we see 1.983. So that's pretty good. I guess we were expecting 1.984, we saw 1.983. And that is a small perturbation, right? It is like smaller than 1% perturbation in the output voltage. Okay, so next we want to replace that 100K load resistor with a 2K load resistor. Now before we predict what we expect, let me just redraw the circuit that we are studying. So our voltage divider is a 3 volt power supply. So we have this 3 volt ideal voltage source, and then we have a 1K resistor that we're calling R1 and a 2K resistor we're calling R2, and we're calling this terminal ground, and then we're calling this the output. And then we've been connecting some kind of a load resistor between this output terminal ground, and we're pretending that this voltage divider all by itself is kind of a black box that we can't peek inside, but we know it's V Thevenin and we know it's R Thevenin. For a device with a linear IV curve, those two parameters characterize the straight line. They give you an intercept and a slope. So basically this is a black box whose IV curve we know. So we can replace that black box with its Thevenin model. I'm probably getting a little bit ahead of the lab exercise. So the Thevenin model for that black box is a perfect voltage source whose voltage is V Thevenin equals, in this case, 2 volts, in series with a resistor R Thevenin, which in this case is 2/3 of a kilo ohm, 167 ohms. And then here is our output node, and here's our other output node, which we're calling ground. So this black box on the right is equivalent to this black box on the left without the load resistor. Then we can connect the load resistor, and the claim is that this black box has the same IV curve as this black box. Therefore, the response of this black box to the presence of this load resistor will be the same as the response of this black box to the presence of this load resistor. And this is pretty easy to determine. You see, we can determine it just by using the voltage divider equation. So this gives us V out equals V Thevenin times R load divided by R load plus R Thevenin. In this case, that would be 2 volts times, well, we're going to make this 2 kilo ohms. So this is 2 kilo ohms divided by 2 kilo ohms plus 667 ohms. That's 2.667 kilo ohms. So we have 2 volts times 2K divided by 2.667K, which equals 1.5 volts. So we expect to see 1.5 volts on the output when we replace this 100K load resistor with a 2K load. Let's try that. Pull out the 100K resistor, and I'll reach into the parts drawer and find another 2K resistor, and red, black, black, brown, so it is a 2K resistor, and I'll plug the bottom end to ground, the top end to this output node, and we see 1.499 volts, 1.5. Now you might say that was kind of a stupid way to get the predicted output, because if you look at this, this is 2K, this is 2K. So 2K parallel 2K is 1K, so you have a 1K, 1K voltage divider, right? Because you can combine these two resistors together to form 1K. So this is 1K up here, effectively 1K down here. So you take this 3 volts and you're basically just dividing it in half with a 1K, 1K voltage divider. That seems like a much simpler calculation than all of this stuff with the Thevenin model. And that is true. In this case, that is a much simpler and more direct calculation. But we want you to be aware of this idea of a Thevenin model. And the Thevenin model is a way to characterize a device whose IV curve is a straight line. And you can characterize it with an intercept and a slope. The intercept is V Thevenin, the slope is R Thevenin. And then the place where you intercept the current axis is called I short circuit. And the idea is, if I have a voltage source whose voltage, when I draw negligible current from it, is called V Thevenin, and I want to know, well, will plugging in a given load resistor make a big difference in the output voltage? This is sort of like the question, can my flashlight battery start my car versus can my car battery start my car? So if I want to know, will the presence of the load make a very large difference or only a very small difference in the output voltage, I say, well, how does R load compare with R Thevenin? And if R load is much, much larger than R Thevenin, then that difference is negligible, because it's R load over R load plus R Thevenin is the factor by which I multiply V Thevenin to get the actual output. So you say, if R load is much, much larger than R Thevenin, you say, well, the voltage doesn't change much, so I don't have to think too hard. But if R load is comparable to, or worst case even smaller than, R Thevenin, then you have to do a little bit more work to figure out how much does the presence of that load decrease the voltage supplied by this black box whose IV curve we've characterized as a straight line with these two parameters, V Thevenin and R Thevenin. What value for the load resistor would bring V out down to half of its original unloaded value? Do not do a brute force calculation. Well, that means we want to choose R load such that this factor equals 1/2. This factor equals 1/2 if R load equals R Thevenin, because then you have 1 over 1 plus 1. So I think if we choose R load equals R Thevenin, then we should get V out is 1/2 of V Thevenin. Let's see how close a resistor we can find in the back room to 667 ohms. I found 680 ohms in the back room. This is such a tiny resistor that it's really very hard for me to see the stripes. I'm going to take this second meter that we've been using to measure currents, and I'm going to configure it to measure resistance by moving this red wire over from the milliamps plug to the ohms and volts receptacle, and then I will put it in ohm mode. I guess I'll drop the little red and black wires that are in the spring clips, and I see 679 ohms. Actually, it says 0.6785 kilo ohms. Okay, so this is 679 ohms, pretty close to 667. So I'll pull out the 2K resistor. I'll put in this 680 ohm resistor, and I think what we see here will become 1 volt. 1.010 volt. Okay, cool. So this is actually a very useful rule of thumb to remember. If you make the load resistance equal to the Thevenin resistance, then the output voltage you get is 1/2 of V Thevenin. And that, in fact, if you have a circuit which really is a black box, so maybe you have a battery, you want to know how much current it can supply, or maybe you have some circuit whose schematic diagram you don't have on hand, and you want to understand how strong a voltage source is it, and you make a guess. Well, I think the Thevenin resistance is on the order of 10 kilo ohms. Well, you can plug in a 10K resistor, and if you see the output voltage drop by roughly a factor of 2, you say that makes sense then. R Thevenin is roughly whatever that resistance was you plugged in, say 10 kilo ohms. So it's actually a pretty useful trick. If you have a hypothesis for roughly what R Thevenin is and you want to test it, you just plug in a load resistance equal to that R Thevenin, and if you're right, then the output voltage will drop by a factor of 2. And then I guess you can reverse engineer it. You can figure out what R Thevenin is from the observed ratio of the voltage before and after. There's more to this part of the lab. This is the last part of part 3 here. Now draw and then build the Thevenin equivalent circuit for your voltage divider. Well, the Thevenin equivalent circuit looks like this. Here's V Thevenin and here's R Thevenin. And V Thevenin is V power supply times that bottom resistor R2 divided by R1 plus R2. And R Thevenin is what you get if you replace the battery or the perfect power supply with a wire and then you measure the resistance between these two terminals. Well, this is the Thevenin model. The original circuit looked like this. Here was our power supply voltage, here was R1, here was R2. You see, if we replace the power supply with a wire and then we measure the resistance between here and here, then there are two parallel paths, you see. So between here and here you can go through R2 or we can go through R1. So R Thevenin is in fact R1 parallel R2, and 1K parallel 2K is 2/3 of a K, 667 ohms. So I can actually build this Thevenin model. So I have a 680 ohm resistor right here, so we can use it, and then we can program our programmable power supply to provide 2 volts instead of 3 volts. So I can pull out this 2K resistor, I can pull out this 1K resistor. I can change this power supply so that it is set for 2 volts. And then here is my 680K resistor. And all I have to do is to say, well, you see, there is my power supply, and it is in series with a 667 ohm, or 680 ohm actually, resistor. And now if I measure the voltage here with no current being drawn, because I have a 10 mega ohm input resistance of this voltmeter, it should just be 2 volts. Let's see, 1.996 volts. It's 2 volts. You see, I can measure the other side here. I can measure, go directly up here, well, it can't be lower. I think that's just a fluke. 1.995 volts. Okay. Oh, remember when we loaded the original circuit with 2K, we got 1.5 volts output. So we still have our 2K resistor here. So if I put my 2K resistor between the output and ground, I should see 1.5 volts here. Let's see. Indeed, 1.488 volts. And if I got another 680 ohm resistor, I think you wouldn't be surprised to see that instead of 2 volts, I saw 1 volt here. I guess I could do it, but I think you just won't find it surprising. So I can put another 680 ohm resistor here, and we'll see 1 volt instead of 2 volts. Sure enough, 0.998 volts. And then remember when we put the 100K resistor there in the real circuit. So we can put that 100K resistor back, and we should be back to 1.986 roughly. So here's the 100K resistor. Okay, 1.981 volts. In what sense is the Thevenin equivalent circuit equivalent to the original circuit? Well, it is equivalent in the sense that it has the same IV curve. Same IV curve. Okay, so any voltage source, well, any two-terminal device whose IV curve is linear can be characterized by a Thevenin model. So this is V Thevenin, this is I short circuit, and this slope is minus R Thevenin. So the original voltage divider and the Thevenin model for the voltage divider have the same IV curve. This is V out, this is I out. So the V out versus I out curve for the Thevenin model is the same as the V out versus I out curve for the original voltage divider circuit. So the whole point of a Thevenin model is to take the original circuit, characterize it by this 2-parameter straight line, and then redraw it as just a perfect voltage source in series with the resistor, because then you can simply use the voltage divider equation to characterize the response of that circuit to the presence of some load connected downstream. You probably think this seems like an awfully complicated way to analyze circuits that would have been much more straightforwardly analyzed using Kirchhoff's rules, and that is a fair statement. But in electronics, we are often interested in taking individual signal processing components and connecting them one after the other, after the other, after the other in a signal processing pipeline. And you want to know, when you connect two devices to each other, do they play nicely with each other? Do they have a problem being connected to each other? And when you're working with voltage signals, the rule of thumb is that you want the input resistance of the downstream device to be much, much larger than the Thevenin resistance, also known as the output resistance, of the upstream device. And if that's true, then the two devices play nicely together. In other words, the presence of the downstream device does not have a significant effect on the output voltage of the upstream device. So in real-life electronics, we very, very often encounter devices whose output is a voltage, and you want to ask how strong a voltage source is that. And if it's an ideal voltage source, like this DC power supply, then there is essentially zero slope, or extremely tiny slope, to V out versus I out. And then you take, say, your car battery, and let's say it has a very small slope like this. And then you take your flashlight battery, let's say it's a 12-volt flashlight battery versus your 12-volt car battery, and it has a much bigger slope. And you say, okay, see, I can characterize the fact that my car battery is a stronger voltage source than my flashlight battery. Let's say it's the 12-volt flashlight battery and a 12-volt car battery, because effectively the internal resistance of the car battery is much smaller than the internal resistance of my flashlight battery. So that's a way of characterizing how good, how close to ideal, how perfect or imperfect a voltage source is that device. And again, when we build up more complicated circuits that consist of several building blocks wired in series with one another, this idea of simple way to characterize, do these two devices make good neighbors with one another, is important. But it's a very useful analysis technique. So if you feel right now that we are taking what should be a really simple circuit to analyze just directly using Kirchhoff's rules and turning it into some complicated abstraction, I feel your pain. We're trying to show you how the abstraction works, and we will continue to use this abstraction throughout the semester. In fact, this simple voltage divider model that we've been using will be generalized the next week or so that we can unify resistors, inductors, and capacitors into one concept called impedance. So these models that we're using based on the voltage divider concept will occur again and again in the course and will be generalized. So you want to get used to the voltage divider relationship. That finally concludes part 3 of lab 2b. Okay, part 4 of lab 2b. So we've been getting used to measuring voltages and currents with the handheld digital multimeters, and you concluded after the first reading assignment that an ideal voltmeter should have an input resistance of infinity. In real life, we use voltmeters whose input resistance is usually 10 mega ohms. An ideal ammeter should have an input resistance of 0 ohms. In real life, we often use ammeters whose input resistance is on the order of ohms. So it seems as if the meter we've been using for most of our current measurements in the last 2 videos has an input resistance of 2 ohms. The current meter that the lab write-ups intended for us to use, I think, has an input resistance of 10 ohms. We will see that in a moment. Anyway, on the order of ohms versus on the order of 10 mega ohms for the input resistance of our typical voltmeter. Let's see under what circumstances the non-ideal nature of the lab's meters can be seen. Most of the time these meters can be treated as if they were ideal, but it is good to keep in mind under what circumstances you need to think more carefully. So you need to keep in mind the orders of magnitude so that you know whether or not you need to pause and think harder. Let's start by measuring just one or at most 2 points, we don't want it to be too boring, along the I versus V curve of a 10K resistor. Oh, now I'm actually going to follow the directions this time. Use the Amprobe 37XRA handheld meter to measure currents, and use the Amprobe AM160A meter to measure voltages. Actually, so this meter that we've been using to measure voltages so far is the Amprobe 37XRA. So we will use that in this last exercise to measure currents. This meter that we've been using mostly to measure currents is the Amprobe AM140A. It's not the 160A, it's the 140A. But in any case, I know that it has a 10 mega ohm input resistance for measuring voltages, so we will use this to measure voltages, and we'll use this to measure currents. I'm pretty sure the input resistance of this guy on current mode is 10 ohms. So that will allow us to get exactly the results that this lab write-up expects for this exercise. Okay, now we have 2 possible ways to wire things up to measure an IV curve. We saw this last time. We could put the voltmeter in parallel with the series combination of the ammeter and the device under test, or we could put the current meter in series with the parallel combination of the voltmeter and the device under test. And if you do the thing on the left, then you have to ask, well, is the voltage drop across the ammeter tiny compared to the voltage drop across the device under test? And if you use the configuration on the right, you have to ask, well, is the current that flows through the voltmeter tiny compared to the current that flows through the device under test? Now, in the case of a 10 kilo ohm resistor, either configuration is just fine, because you know that 10 kilo ohms is a few orders of magnitude bigger than the series resistance of the current meter, and you know that 10 kilo ohms is a few orders of magnitude smaller than the parallel resistance of the voltmeter. So the presence of the meters will make something like 0.1% difference in either case. So it's going to be a difference that's too small for us to notice. So I guess we'll see that it won't make any difference which of the two configurations we use. When we're just measuring the IV curve, we'll just measure a couple points for a 10K resistor. And then we're going to go on and do something more surprising. So we happen to have a 10K resistor that we were using earlier. So it is brown, black, black, red. And then there's the brown 1% stripe on the right. Okay, this red wire is coming from my programmable DC power supply. And this is ground. So we can leave those in place. We'll pull out our meter for the moment. Here is our 10K resistor. I will connect one end of the resistor to ground, as is done in both diagrams here. And I'll put the other end of the resistor at this breadboard node. Now let's try the option on the left. So here's the power supply. So we want to measure the power supply voltage with the voltmeter. We're going to use this one this time as the voltmeter. So I'll take my little red wire and black wire, and I'll connect the voltmeter between the breadboard plus voltage and the breadboard ground. And then I'll turn this on to DC volts mode. It reads 0 right now because the power supply is off. Well, it really reads 0.0010 volts. Then we'll use this one as our current meter. So I have to move the red wire from the volt ohms position over to the milliamp position. So I can do that. And then I'll see it beeps at me until I am in a compatible mode. So I'll put it on the milliamp mode. Then I'll take the two wires, and we want to make the current flow from our voltage source to the resistor under test through the current meter. So that's what we did here. So this current meter has current going in up at this top row that we're using as our voltage source, and then coming back out the black wire, which is in this breadboard column here. That breadboard column contains the black wire of the current meter and then the top lead of the resistor under test, which is a 10K resistor. And then the bottom lead of that resistor under test goes to ground. Okay, 10K resistor. So if I do 1 volt and I turn this on, then I see 0.1 milliamps. So there's 1.0006 volts, 0.100 milliamp. I can do 10 volts, 10 volts, and I see 10.002 volts and 1.000 milliamp. This will probably get boring if we do too many more points. We could do 5 volts. 5 volts. We see 5.003 volts and 0.501 milliamps. So I think that makes sense. But now let's try the same resistor with the right-hand configuration. So I'll turn the power supply voltage off. Instead of having the voltage meter directly measure the power supply voltage, instead the voltage meter will directly measure the voltage across the resistor. So I'll take the voltmeter, which is plugged in here, so that's this voltmeter, and I will instead put it across the resistor. So there's the red lead, there's the black lead. Okay, so now we are in this right-hand configuration. It's a little hard to see, but this breadboard node, this little column of 5, it has the top end of the 10K resistor, it has the black end of the current meter, and it has the red end of the voltmeter. Then this row up here contains the red end of the DC power supply and the red end of the current meter. And then this lower row contains the ground end, the black end of the DC power supply, contains the black end of the voltmeter, and it contains the lower end of our 10K resistor under test. So I can go to 1 volt and turn this on, and we see 0.1 milliamp and 0.9995 volts. Okay, so actually we did see a tiny little difference. We see 0.9993 volts instead of seeing basically 1 volt, because there is a tiny little voltage drop across the current meter. But basically, okay, 0.1 milliamp. We can go to 10 volts, 0 volt, and we see 1.001 milliamp, and this is 9.991 volts. So it does seem like we see something like a 0.1% effect, because it's like 10 ohms out of 10 kilo ohms. So we do expect to see a 0.1% effect. And then we can go to 5 volts, and we get 4.997 volts and 0.501 milliamps. So it does make a noticeable difference, but it's a 0.1% difference. So it's basically a negligible difference. The fact that there is a 10 ohm input resistance of this current meter. Now we're going to do something a little bit more surprising. We're going to try the same exercise. Instead of for a 10 kilo ohm resistor, I think it's going to be a 1 mega ohm resistor. Let me see. Now replace the 10K resistor with a 1 mega ohm resistor. Be sure to measure its resistance with the ohm meter first, and set the power supply for 30 volts, which is as high as the power supply goes, and then try options 1 and 2 again. Okay, we want to remember that the digital voltmeter's input resistance is 10 mega ohms, and the 37XRA current meter's input resistance when in milliamp or microamp mode is 10 ohms according to the manual. Let's give that a try. And while we're giving it a try, we want to make a note of which option is better suited to simultaneously measuring the voltage across the resistor and the current through the resistor, and why is that true? Okay, here is a 1 mega ohm resistor. Okay, you might be able to see brown, black, black, yellow. And then there's a space, and there's the 1% brown stripe. So brown, black, black, yellow. Yellow is, so let's see, black, brown, ROY. Yellow is 4. So that is 1004. That's 100 times 10 to the 4. That's 10 to the 2 times 10 to the 4 is 10 to the 6. So that should be 10 to the 6 ohms. It's a little unfortunate that I have to disconnect part of our circuit to measure the resistance of this thing, but I guess I will do that. So here is the meter that we've been using to measure volts in this part of the exercise. I put it in ohms mode. It's actually still connected to the 10K resistor. I'll pull out the 10K resistor, and then when you measure resistances of things, you want to make sure that those things aren't connected to anything else. So if you already have a resistor wired up in your circuit and you apply the ohm meter to measure its resistance, that will usually give you an underestimate of its true resistance, because there could be other parallel paths. You could get even stranger results if there's something powered plugged in. So you usually, to get an accurate resistance measurement, you have to remove the device, the resistor, from the circuit and measure its resistance all by itself. So we see 1.0022 mega ohms right here. So, well, now it says 1.0015 mega ohm. That's funny. Now it says well, okay. It's interesting that I can change the result a little bit just by wiggling the wires. Anyway, okay, it's a mega ohm, 1.002 mega ohm. I think you can sort of get a sense of the precision of this meter. It's pretty good for 10 to the minus 3 precision. It's questionable, I think, for 10 to the minus 4 precision. So 1.002 mega ohms. Now I can put the meter back where it was. We were already in the right-hand configuration, so let's start with the right-hand configuration. So I'm just putting things back the way they were when we were last measuring the 10K resistor. I'm going to put this back in volts mode, and then I'll put the 1 meg resistor where the 10K resistor had been. Okay, so the top end of the 1 meg resistor is in this little column, and the bottom end of the 1 meg resistor is in this ground row. Here is the DC power supply positive end. Here's the DC power supply ground lead. This is the current meter red lead, and then this is the current meter black lead, and then we're measuring between this red lead and this black lead, we're measuring the voltage directly across the resistor. So let me turn on this current meter to milliamps mode, and then I will program this power supply to 30 volts, and I'll push the on button. And you see 30.003 volts, and you see 0.033 milliamps. And let's see, 0.033 milliamps is 34 microamps. So you see, this is kind of interesting. We're expecting 30 microamps, and we see 33 microamps. Why is that? Well, we expect 30 microamps to flow through this 1 mega ohm resistor, but there's an additional 3 microamps flowing through the 10 mega ohms of the voltmeter. So you see, the current we're measuring is not really flowing through 1 mega ohm. It's flowing through 1 mega ohm in parallel with 10 mega ohms. 1 mega ohm in parallel with 10 mega ohms is about 0.9 mega ohms, roughly. Yeah, so see, if we have 30 volts here, 30 volts through 1 mega ohm would be 30 microamps, but then that same 30 volts through 10 mega ohms would be an additional 3 microamps. So we have 30 plus 3 is 33 microamps. So that's pretty interesting. So we get 10% more current than we expected because we have to account for the current that flows through the voltmeter. Okay, that was interesting. Now let's try the other configuration, the left-hand configuration. In this case, we want to measure the voltage across the power supply. So we'll take the voltmeter, which was connected just across the resistor, and we will instead connect it across the power supply. So now we see 30 microamps. So there's 0.030 milliamps, or 29.9 microamps. So we see 30 microamps, the expected current, and we see 30.002 volts. So in this case, the 10 ohm series resistance of the current meter is negligible compared to the 1 mega ohm resistance that we're trying to measure. So this voltage drop is completely negligible compared to this voltage drop. So when we measure the voltage between here and here, it is negligibly different from the voltage across the resistor under test. By contrast, if we want to measure the current through the resistor, it really makes sense to use this left-hand configuration, not the right-hand configuration, because the current that will flow through the voltmeter is not negligible compared to the current that flows through the resistor. Whatever current flows through this resistor, well, this is a 1 meg resistor, so 1/10 that current will flow through this voltmeter, so we'll get a current which reads back 10% larger than the current that's actually flowing through the resistor. So this is not a terribly accurate measurement of the current through the resistor because there's this alternate path through the voltmeter which is non-negligible. So this is just supposed to illustrate for you that when using the lab instruments, you need to bear in mind their limitations. Usually, for most purposes, the series resistance of this current meter is small enough to be completely ignored, and usually the parallel resistance of this voltmeter is large enough to be completely ignored. But you need to keep in mind the orders of magnitude so that you know when you need to pause and think and say, oh gee, the 10 ohm series resistance of this current meter actually matters. Let me go back and see how big an effect it is. Or, oh gee, the 10 mega ohm input resistance of this voltmeter actually matters. And we will see a couple weeks from now, when we use this signal generator, that this signal generator actually has a 50 ohm output resistance. So if you are using this signal generator, which we don't know anything about yet, but you're using this, we'll often use this as a signal source. And when we use this as a signal source, you have to be aware of what is the input resistance of what you're plugging this thing's output into. There are a couple of labs where you plug the output of this thing into something whose input resistance is like 1,000 ohms, and this is 50 ohms, and you actually get a 5% correction. You say, why are things 5% different from what I was expecting? And it is the comparison of the 50 ohm Thevenin resistance of this signal generator to, in this case I'm just describing, waving my hands, the 1 kilo ohm input resistance of the circuit under test. So again, it's important to keep these orders of magnitude in mind so that you know when to expect to have to work harder and when you know you don't have to work harder. There is one more part of this exercise. Now set the power supply down to 0 volts, replace the resistor with 10 ohms, and then carefully dial the power supply up to 1 volt. We're going to keep the current well below the 400 milliamp limit of the meter. So now let's see what the difference is between options 1 1 and 2. So we're going to try replacing this 1 mega ohm resistor with a 10 ohm resistor, and we'll go back and try these two configurations. First, I'm going to turn this power off, and I'm also going to set this to 0 volts. And I'm going momentarily to turn the meters off so that while I go into the back room, I'm not draining their battery. I found in the back room two different styles of 10 ohm resistor. The one that you see on top is a 5% tolerance 10 ohm resistor. So it is brown, black, black, gold. So brown, black, black means 100. So that's 10 times 10 to the 0. And then the gold stripe on the right means it's a 5% tolerance component. The one on the bottom is a 1% tolerance component. Brown, black, black, and I think that's a gold stripe. And then brown, so this brown stripe on the right is the usual 1% tolerance indicator. But I think this gold stripe basically means -1. So it's like 1, 0, 0, and then a -1. So that is like 100 times 10 to the -1, so it's 10 ohms. So I guess we expect this one to be within 1% of 10 ohms, and we expect this one to be within 5% of 10 ohms. So let's measure them both with the ohm meter. So I'll take this meter and put it on ohms mode, and it is going from here down to here. This would be 0. Okay, so if we measure the 5% tolerance resistor, we see 10, well, it's actually pretty good. Okay, 10.14 ohms. So it's only 1.3% away from the nominal value. Okay, 10.13 ohms. That's okay, good. And if we take the other one, this should be within 1% of 10 ohms. Let's see what we get. 10.15 ohms, 10.14. That's interesting. I'm going to go to the back room and measure both of these resistors with the fancy resistance meter we have in the back room. I'll tell you whether they say anything different. Well, somewhat interestingly, the fancy meters in the back say something like 9.91 or 9.92 ohms for each of these. When measuring such small resistances, you have to think about what is the resistance of the wires between the meter and the device whose resistance you're measuring. So I think if we measure the resistance of just the wires here, we get 0.3 ohms. It says 0.25 ohms. So I guess we expect to slightly overestimate the resistance of something so small here. So this says 10.2 ohms basically, but we saw 0.3 ohms, saw 0.2 ohms just in the, we saw about 0.2 ohms just in the wires. So then we see 10.15 ohms here. So I guess that would, if we subtract, we get 9.95 ohms. Anyway, pretty close to 10 ohms. It is interesting, when you're trying to measure really small resistances, you have to worry about the resistance of the wires that you use to make the resistance measurement. So we will put our 10 ohm resistor into this circuit where the 1 mega ohm resistor was a moment ago. We are pretty much already set up in the left-hand configuration. So the voltmeter, well, we disconnected the voltmeter. We want to reconnect the voltmeter. The voltmeter should go across the power supply, and the current meter is in series with the resistor under test in this left-hand configuration. So the current meter is going from the power supply to this node where everything meets, the node here. So we can turn on the current meter to milliamps mode, and the power supply is off. So I guess this thing says 0.05 milliamps. I think it's, oh, I see. Haha, there really is a little bit of a current running because I left this thing in ohms mode. That's really funny. So we're measuring the current that the ohm meter is forcing to flow. So let's put this into DC volts mode. Gee, we still see 0.05 milliamps. Oh, that's interesting. So it turns out it must be this DC power supply, even when it is off, is still causing some small current to flow. I pull this out, and now I read 0. And I push it back in, and I read something non-zero. What if well, that's pretty interesting. Okay, so we will set this to 0 volts, and I'm going to turn it on. Oh, that's interesting. So I turn it on to 0 volts, and now I get 0 current. So I'm not sure exactly what it's doing when it thinks it is off. Now we're going to, here, let me Maybe I'll zoom in so you can see what the readings are here. So I'm supposed to gently increase the voltage to 1 volt. Okay, so the DC power supply is programmed for 1 volt. We read 0.9948 volts. This voltmeter is connected directly across the power supply, so it ought to give us a correct reading of what the power supply voltage is. Current we read is 46 milliamps. 46 milliamps seems too small. So 1 volt across 10 ohms, we expect 100 milliamps, and instead we see only about 50 milliamps. Why is that? Well, I guess we can guess why. It's because the resistance of the ammeter is about 10 ohms, and this is our 10 ohm resistance, so we really have 20 ohms in series with the power supply rather than the 10 ohms that we are trying to measure. So in this case, the voltmeter is lying to us about the voltage across the resistor, because the voltage that the voltmeter sees is the voltage drop across the ammeter plus the voltage drop across the resistor, and those two voltage drops are comparable in this case because the ammeter's resistance is comparable to the resistance that we are trying to measure. In fact, it's almost equal to it's basically equal to the resistance we're trying to measure. So now let's try the right hand option. That means we're going to move the voltmeter over to be just directly across the resistor. So we'll take the voltmeter and we will put it directly across the resistor. So now, even though the power supply is set for 1 volt, we see 0.458 volts across the resistor and 45.88 milliamps flowing through the resistor. So that makes more sense now because the voltage drop across the ammeter is basically the same as the voltage drop across the resistor. So now we say, okay, the voltage drop across the resistor is 0.458 volts, and the current flowing through the resistor is 45.9 milliamps. Now, how do we know that that's the correct current? Because in principle, there are two paths for the current to flow through. The current can flow through the resistor, and the current can also flow through the voltmeter. Well, this is a 10 ohm resistor, and the voltmeter is a 10 mega ohm resistor. So 10 mega ohms is like 1,000,000 times as large as 10 ohms. So that would be like a 1 in a million correction to the current. And you know, we only have 4 decimal places here. So we can safely say that the current flowing through the voltmeter is completely negligible on this scale. So in this case, there is a clear choice to make. The right-hand option is much better for giving us a sensible simultaneous measurement of the voltage across the resistor and the current flowing through the resistor. So I think that was also pretty interesting. In this case, we had to consider the voltage drop across the ammeter compared to the voltage drop across the resistor we're trying to measure. In the previous example with the 1 mega ohm resistor, we had to consider the current flowing through the voltmeter in parallel with the current flowing through the 1 mega ohm resistor we were trying to measure. So again, most of the time, the lab instruments will give you results that you can just take at face value, but it's important to bear in mind the orders of magnitude of the lab instruments' input resistance or output resistance. Output resistance is another word for Thevenin resistance, so that you know when you have to pause and think more carefully. Okay, so I'll turn everything off. So that was lab 2b. And I think I have to give you some guidance that tells you not to write down too much detail. I don't want this to take up too much of your time, but I think there are some observations here that are worth your kind of looking at and pondering. So I have to somehow give you just the right guidance so that you actually think about everything that you saw me do in this video, but you don't spend really any more time writing things up than it just took to get through watching the video and pausing every now and then to think about something. So we're going to have one more lab to get through in video form, and then finally we can meet together next week in our real classroom.